Good morning, good afternoon, and good evening, wherever you are in the world. I hope this presentation finds you safe. Welcome to using the Fast Fourier Transform Beyond Spectrum Analysis at the DSP online conference. My name is John Edwards. So for those that don't know me, if you're thinking I'm the former US Senator John Edwards, who was involved in a little tabloid scandal that ended his race to the VP candidacy, unfortunately there won't be any salacious gossip in this presentation. I am a DSP, AI and embedded systems consultant. I've been working in this field of DSP for over 30 years now. I was very fortunate. I started in the very early days of digital communications, wireline communications with the old V-series modems. And over the time I've worked on 3G and 4G base stations and mobile devices, audio systems more recently, and in the last year or so, an increasing amount of machine learning, particularly for vibration and machine analysis. I'm a member of the IET and the IEEE in America, regular contributor to papers at DSP conferences, and present several training courses, often bespoke DSP training courses to companies. And I'm also a visiting lecturer at Oxford University. So if you need any assistance with your DSP or your AI machine learning projects, then please do get in touch. Okay, so this talk we are going to discuss several applications of the Fast Fourier Transform beyond just using the Fast Fourier Transform for spectrum analysis. We're going to, for the majority of the talk, we are going to look at using the Fast Fourier Transform for analyzing signals and processing signals in different ways, and look at the benefits of using the frequency domain for implementing our processing systems. But to start with, we're going to look at some pre-processing that we can do prior to calling the Fast Fourier Transform, and we're going to look at an algorithm called the Zoom FFT. So I'm sure many people on this presentation are familiar to some degree with using the Fast Fourier Transform for spectrum analysis, whether you're implementing this using your own code, you're using the FFT function on a signal analyzer, an oscilloscope, for example. All spectrum analyzer applications are typically based around the 6 or 7 processing blocks shown in this diagram. It's a very common processing chain for the Fast Fourier Transform. But as I say, this is not the only application for the Fast Fourier Transform. So we're going to look at how we can use the Fast Fourier Transform in different application areas, starting, as I mentioned, with the Zoom Fast Fourier Transform. The Zoom Fast Fourier Transform is a much misunderstood algorithm, I think. Some people seem to think that it is a very complex algorithm to use. Certainly in the older days of DSP, you'd often see on internet forums that you have to be a super guru of DSP to be able to use the Zoom Fast Fourier Transform. I don't actually believe the case, so I'm going to talk about an application of the Zoom Fast Fourier Transform. This was an application I was involved with many years ago, where we were trying to detect the size of suspended bubbles in fluids, actually in the ocean. using ultrasound signals. And the system, the test system that I was working on, development system, basically used underwater moving coil loudspeakers and an underwater ultrasound generator to generate acoustic signals that would impact on the suspended bubble, and then the results of that interaction would be picked up by a piezoelectric immersive transducer. Now you may think, well, how would a bubble impact the acoustic signals? And the answer is that the bubble acts as a nonlinear signal, very much like a diode in a radio receiver. So it turns out that the bubble will have a resonant wavelength, which is approximately equal to 3 times the bubble radius in meters. So you could try this in the bath tonight when you get home, or most of you are probably locked down and at home, so you can try it in the bath later. But for the bubble sizes that we were measuring in this application, we required a 1 megahertz ultrasound carrier signal and a 50 kilohertz bandwidth of signal that we needed to analyze. So the audio and the ultrasound signals were impacting on the bubble, creating a signal at 1 megahertz, which is the carrier frequency, and the modulation bandwidth was 50 kilohertz. So in this application, we used an off-the-shelf A to D converter that ran at 3.3 megahertz, so nicely oversampled from our high frequency carrier system. But if you think about requiring a suitable resolution of a 50 kilohertz bandwidth when a sample rate of 3.3 megahertz is used, it turns out that you need a very, very large fast Fourier transform, about 500,000 points. That's quite unfeasible. It would take a long time, a lot of memory, a lot of MIPS, etc. So the solution that we used was to use the Zoom FFT to modulate down our 3.3 megahertz signal to a baseband signal of 50 kilohertz, and then we would perform our fast Fourier transform at 50 kilohertz. And this nicely led to an FFT size of 8,192 points, which is nicely achievable. Actually, as an aside on this project, if we did the maths, the ideal fast Fourier transform size would have been 10,406 points to get the desired resolution of the application. So we explained to the customer that you can either have 8,000 points or 16,000 points. I know there are some other points in the between that you could use, but to keep the processing simple, we stuck to our powers of 2. We explained the cost difference in terms of the processors, the MIPS and memory and so on, and it was decided that a compromise of 8,192 points would give a perfect or an acceptable resolution to the frequencies. Okay, so this is the goal of the project. We're going to use the Zoom FFT to zoom in, as the name suggests, on our particular frequency band of interest. Excuse me. So this is a diagram that explains the process of undersampling, or subsampling as it's sometimes called. It is just an amplitude modulation task of bringing the signal down from the carrier frequency, which in this diagram I've shown as 1 megahertz, so it's actually 3.3 megahertz, down to baseband. And the key things that we have to watch are, to avoid aliasing, we need to ensure that our baseband sample frequency, FS, is greater than the bandwidth of our modulation signal. And also, to avoid spectral overlap, we need to ensure that the modulation signal that we're bringing down to baseband meets the folding functions shown in here. So the lower frequency must be greater than the sample frequency over 2 multiplied by k, which is the folding integer, and the higher frequency must be less than k plus 1 times fs over 2. What does this mean? Basically, k is the folding integer. If k is an even number, then we get a nice spectrum down in the baseband, and if k is odd, then we get spectral reversal, which is actually easily removed. So sometimes if k being odd gives an easy fold down from the carrier frequency to baseband. So in this case, we mixed down to baseband using an appropriate k factor, and we ended up with our nice 50 kilohertz bandwidth at baseband. Okay, so let's have a think about this process of downsampling and how it has benefited our application. If we think about we've simplified it here, but if we think about the original scenario where we have a high sampling frequency, then supposing we just have to implement a very simple low-pass filter in baseband, but with an oversampling frequency fs1. The number of MIPS we require depends on the hyperparameters, the steepness of the filter roll-off, and also the sample rate. The higher the sample rate, the more coefficients we're going to need for our filter. In this example, if we manage to reduce our sample frequency from fs1 to fs2, in this case by a factor of 4, then clearly reducing the sampling frequency will give us more time between samples, so that we require less MIPS to implement the same filter. But if we think about stretching this new sample frequency out to match the original one, what we see now is that the characteristics of the filter, i.e. the roll-off, have been massively reduced. So it turns out that reducing the sample rate always gives you a square law relationship between the sample rate and the number of MIPS. So if you can reduce the sample rate by a factor of 2, then the number of MIPS required reduces by a factor of 4. If you can reduce the sample rate by a factor of 4, the number of MIPS required improves by a factor of 16. So in telecoms in particular, reducing the sample rate has a very, very large impact on the number of MIPS required. So let us have a look at how we're going to do this in the Zoom FFT. In this particular application, we were sampling our audio signal from our piezoelectric emissive transducer, and that was coming in as our input signal xk, and then we were multiplying it by our modulation function, just simply amplitude modulation, but complex. So we've got the cosine for the in-phase or the real channel, and the sine for the quadrature or the imaginary phase signal. We then filter our signal down to baseband, where we perform our 8K point FFT that we talked about earlier. Now we'll look at the filters in a second, but the things we have to think about in this application are that the primary driving function really is the input sample rate, 3.3 megahertz. We're going to be putting data at 3.3 megahertz through this modulation function and then into our filters. These filters have to be very, very simple at the front end. So we use a very specific type of filter, a cascaded integrated comb filter that we'll look at in a minute, sometimes called a comb filter or high decimation filter. And these filters are purely there to reduce the sample rate using the factor that we talked about earlier. By the way, between the decimation process and the Fast Fourier Transform, we have our windowing function. And in this case, I used a Blackman-Harris window. It's pretty much my default window for all processing when I am doing general purpose DSP applications like this. And of course, we're very pleased that Professor Harris Fred Harris is also a co-presenter at the DSP Online conference this week. Okay, so let's have a think about the filtering requirements we've talked about. The key thing is that these filters have to be really, really simple because the processor at the front end is running at the data rates at the front end are running at a very high frequency. So we use a type of filter I've just mentioned, the cascaded integrated comb filter. These are linear phase filters. They're commonly used in this kind of interpolation or decimation application. And the key features are they do not use multipliers. Multipliers are very expensive in terms of transistors, power consumption, and so on. They have a very small memory requirement, and they have very low latency as well, which is good in real-time applications. Hence, cascaded integrated comb filters are very commonly used in these high sample rate systems. So let's have a look at the cascaded integrated comb filter. I'm not going to go into a massive amount of detail in this presentation. I'll give an overview. If you want to get some real good detail on cascaded integrated comb filters, I thoroughly recommend you Google CIC followed by the name Rick Lyons. Rick really knows his stuff when it comes to DSP. He's written one of the great DSP books. I still use it in my class for teaching at University of Oxford. And if you look at the DSP related website, you can see some great articles from Rick that discuss CIC filters in all detail. But for now, what we're going to do is look at the basics. The key things are that, as you can see from these diagrams, the integrator and the comb section of the filters are very, very simple. Each element consists of a delay, which is always a unit delay in the integrator, but can be a multiple element sample delay in the comb section. But in the integrator, it's a unit delay, so a single memory location followed by an integrator. In the comb, you've got the delay of m samples and a subtract operator. So actually, mathematically, just a single operation, either an addition or a subtraction. So very easy to implement, very low MIPS. But if we think about these algorithms, you might think, whoa, this is interesting. So we're running our high-speed data into our integrator, which is constantly adding numbers together. What about numerical overflow in the integrator? Well, it turns out that if we used a fixed point number scheme in our processors, then overflow is good. And in actual fact, when you configure your processor, because some processors you can configure the ALU for rollover or clipping fixed point number operations, you need to ensure that the numbers will roll over. Because if you think about it, in a positive half cycle, your numbers will, of a sine wave sinusoid, the numbers will roll over. But then in a negative half of your sinusoid, the numbers will roll back, and over a long period window, the numbers will work out. So let's have a quick look at how we would implement our decimators or interpolator structures. Basically, we cascade our integrators and our comb filters. For the decimator, we have integrators followed by sample rate reduction, followed by comb filtering, and in our interpolation, we have our comb filtering followed by our sample rate increase, followed by our interpolating integrating filters. And as you can see from the diagram here, the end result of a decimating CIC filter is that we get a nice low pass filter that we can pass on down the stream. Typically, we would then, having performed the first stage of high decimation filtering, we would follow that with a standard low pass filter that would do some passband gain normalization. And actually, you can see that here. We've tried to flatten the response in the passband using an FIR filter. Okay, so in this application, it was implemented on a multi-processor DSP system, and this just shows how we partitioned the processing. The first DSP implemented the continuous streaming process of the modulation and the filtering, and then the second CPU was responsible for the block-based processing, the filter, the FIR filtering, the windowing, and the Fast Fourier Transform. Okay, so there's a summary of the system. Very simple to use. I've used the Zoom FFT in a number of applications over the years, and it does make life very easy. It's a great algorithm to go and research and to learn about modulation, filtering, and a lot of other techniques related to DSP. Okay, so having talked about pre-processing data before the Fast Fourier Transform, let's have a think about now for the rest of the lecture using the Fast Fourier Transform to enhance other time domain algorithms. The first application we're going to talk about is frequency domain filtering. And I'm sure many of you are familiar with time domain filtering. And the typical cascaded bucket brigade FIR filter. If we look at the maths, and this slide really sort of compresses the first chapter of almost every DSP book that's available, where we talk about linear time invariant systems or processes. If we have our input sequence in the time domain passing into a system, it could be any system, a machine, a control system, a filter, or any kind of control system, will have an impulse response. And if we want to calculate the output mathematically, y of t in time, then y of t is equal to the convolution of the input sequence x of t with the impulse response of the system h of t. That's a constant time process. So in the FIR filter example, the impulse response is the coefficients of the filter h0, h1, h2, etc., etc. So the coefficients define the impulse response of the filter. But if we look at this block diagram, we see that actually for every input sample, x of t, x of n, every input sample, we have to multiply all of the delayed time domain samples with the coefficients, sum the results to get the output. That's a lot of maths for every input sample, especially if we have a long filter. So we can use a property of signal processing that convolution in the time domain is equivalent to multiplication in the frequency domain, and also vice versa actually. Convolution in the frequency domain is equivalent to multiplication in the time domain. But for our purposes, we're thinking about convolution in the time domain, which is this very mathematically or processor intensive task: multiply, accumulate, multiply, accumulate, multiply, accumulate. We can replace that convolution operation with a multiplication operation in the frequency domain. So how do we do that? Well, we would need to transfer our time domain input sequence to the frequency domain using the discrete Fourier transform. We then can perform our operation in the frequency domain, which is a simple cross multiplication, dot product of the two vectors. Then we can convert our frequency domain result back to the time domain using the inverse fast Fourier transform, and now we have our output. So now we think, if we think about this, we have a trade-off. The direct path requires a lot of MIPS and memory. The indirect path requires that we take an array of data, we convert it to the frequency domain, we then do our very simple multiplication, and then we pass the data back to the time domain using the inverse fast Fourier transform. And now we get our output. So the trade-off here is that we've massively reduced the number of MIPS required for this indirect path, but the cost is that we have a much longer latency, because in this input stage we have to acquire a number of samples equivalent to the length of our FFT. We'll look at this in a minute. And then on our output, we also have to have a delay while we stream out the buffered data from our inverse FFT. So the benefit, again, is increased or reduced MIPS. Our cost function is that we have increased latency. So here's a diagram of the DFT. I'm not going to go into it in any detail, because I'm sure pretty much everyone on here is familiar with the DFT, the Fast Fourier Transform, as it is the usual implementation. But to say it, just to use it to remind you that this is a block-oriented function. We acquire an array of data in the time domain of big N samples. We then perform the DFT or FFT operation to get that sequence from the time domain to the frequency domain. And it's all processed as a block of data, so it's not a streaming application like the FIR filter. Okay, so let's have a look at how we could use this in our filtering application. The first thing is that if we think about two arbitrary inputs, we've called them A and B here, and one of these could be our coefficients. Let's say A is our real-time input stream and B is our filter coefficients, as per the transfer function before, diagram before. We translate the audio stream or the real-time stream and the coefficients into the frequency domain, where we do our cross multiplication, inverse FFT, and we get our output. Now, in the case of filtering, of course, the first thing that we can do, if input B is our coefficients, we can pre-calculate those at build time, at development time, to calculate the frequency domain coefficient. So that that massively reduces the computational MIPS requirement. The second thing is, I apologise, my picture is sitting over the top of some of this text, but you'll be able to download the PDF file from the website and see the missing text. But the other thing is that a side effect of the fast Fourier transform is that we need to use bit reversed addressing either in the time domain or the frequency domain, depending on the algorithm that you choose. Now, I'm not going to go into bit reversed addressing in this slide, but needless to say, if we use the appropriate fast Fourier transform, which is called the decimation in frequency fast Fourier transform, then the data shown highlighted in red is in bit reversed format. If we handle all of the data in bit reversed format in the frequency domain, we don't need to de-reverse it, then reverse it again. We'll just leave all of the data in bit reversed format, process it in bit reversed format, and then we would again use the decimation in frequency inverse FFT to get the output sequence that we are looking for. So again, using bit reversed ordering allows us to significantly reduce the MIPS requirement of our application. Okay, so how do we allow for the fact that we've got this continuous time input sequence in the time domain? We want a continuous time output sequence in the time domain, but in the middle we've got this block-oriented approach in the frequency domain. Well, the solution is that we use one of two methods. They're overlap methods. One is overlap and add, one is called overlap and save. That's what we're going to look at in the next few slides. In the overlap and add implementation, we have our continuous time sequence that we are going to split into our n samples, which is the block that we're going to pass to our fast Fourier transform. We're going to process the data in the frequency domain of these n sample blocks, and then when we get the output blocks coming out of the inverse FFT, the overlap sections, we are going to sum the results. So let's have a think about this. Our fast Fourier transforms, if we take two blocks of data, our n samples of our time domain and our m, big M, let's call them coefficients of our filter, if we convolve independent arrays of data, then the output array length would be the sum of the two input array lengths minus 1. So n input time domain samples, m input coefficients, convolve together, the output length is n plus m minus 1. So the output length is always more than the input length. That's how block-oriented convolution works. So this is why we have to do the overlap and sum of the data so we don't miss anything. Now, there is one other point that's worth mentioning because of this. The question is to pose is, what size fast Fourier transform do we require in that application? There's a note about it in the slide. Basically, the key thing to remember is that the fast Fourier transform must be greater than this length n plus m minus 1. There's a note in the slides about it. So anyway, for the overlap and add implementation, we have these output sequences that are longer than the input sequences, and the way we've written the code means that we add those overlaps together and we get our filtered output continuous sequence. And the results, not surprisingly, are exactly the same if we go via the direct path or the indirect path, the results, of course, they're exactly the same. The only difference is the extra latency of the fast Fourier transform based approach. Okay, so if you want to have a look at the code, here's the code. 5 simple functions. Input fast Fourier transform for our source data. Remember, we've already pre-calculated the coefficients array. Our complex cross multiply, inverse fast Fourier transform, sum the overlaps, and then copy the output result. Copy the overlap array to like a side array to be used on the next iteration for that add operation. So these two functions are like a loop. You add in the previous overlap, and then having generated your output, you then copy the array to be used in the next overlap. Okay, so actually the overlap and add operation is very simple. Just use FFTs, cross multiply, and then add the data and copy the overlap buffer. So I said that there were 2 approaches. One is overlap and add, the other is overlap and save. In the overlap and save method, the pre-roll for the filter is discarded rather than being added into the convolution output operation. So we would discard the pre-roll. So let's have a quick look at the code. Again, 5 very similar functions. We copy the source data with overlap. We perform the fast Fourier transform, complex multiply, and inverse fast Fourier transform, and then we copy the output data, just the block, without the pre-roll, so that we just take these chunks of data and we output those to our onward stream. So very simple, similar process to the overlap and add. Because they're so very simple, when I've implemented these in the past in a couple of applications, I've just tried both and see which requires the least amount of MIPS, which in my previous experience has been the overlap and save, because it doesn't require that addition operation. But they're very similar, very easy to implement. If you've got one, then you'll be able to try the other and see which is best for you. Okay, so that's the frequency domain convolution. There's the note about the required FFT length. There are some big computational savings to be made using this, especially when we pre-compute the convolutional kernel. For the filter coefficients, gives us even more efficiency. Here's a slide I did actually many years ago when I was looking into the trade-off. This isn't for a specific DSP, and for different devices the numbers will vary. But what I basically found was that for very small filter lengths, up to about 64 points, then just using the standard time domain convolution required less MIPS than the frequency domain approach. But once you get to much larger filters, certainly once you get up into the hundreds of coefficient filter lengths, then you find that the frequency domain approach wins massively. Okay, as a side note, a final little side note, we can also perform frequency domain correlation using exactly the same technique. We just need to complex conjugate our input for our reference sample set. We'll come on to look at correlation in a little bit later in the presentation. Okay, so the next application I'm going to talk about, is an ultrasonic time of flight application where we're going to use the Fast Fourier Transform to improve the resolution of distance measurements using ultrasound signals and interpolation. So in this application, I didn't implement this. A colleague of mine, Gordon, implemented this. He's totally responsible for all of the technical detail here. But in this application, an ultrasound transducer is being used to send pulses of signals through sheet steel, and using a correlation approach to detect the thickness of the steel from the time of flight of the ultrasound signal through the steel. So in this application, the steel it's a real-time production system, and the pulses are they run continuously, but there's a pulse repetition frequency of about 1 kilohertz. So there's 1 millisecond between pulses where we can analyze the reflections of the pulses that are transmitted. It's nice in these applications to be able to detect residual stress in the crystalline structure of the material being analyzed, but this requires very high resolution time of flight measurements. So how can we, let's say, improve the time of flight measurement in our system? Here's a high-level view of the system. Again, this happened to be a dual DSP application, just because of the number of MIPS required to handle the real-time data. What we need to do is, when we sample our received pulse, the samples are shown by the black crosses in the diagram here. The samples are clocked on the positive going edge of the clock going to the A to D. And we want to improve the resolution of this particular application to detect the peak of the pulse. Now, it's also very common in many applications to be able to detect the zero crossing point. And actually, this technique is also very common in applications where you need improved zero crossing detection. So the same technique works for both improved zero crossing and improved peak detection. Now, we could use an oversampling FIR filter to interpolate the red cross samples shown in the diagram. But again, we have the same problem that we've had in some of the previous examples, where time domain filtering is a very expensive process. So let's have a think about how we can use the frequency domain to improve the resolution. Now, in this application, we're sending out these pulses, so we have this frame of data, this 1 millisecond frame of data, where we're looking at the reflections. We have a frame-based approach, which, as we've discussed, is ideal for FFT-based applications. So what do we need to do? Well, we need to take this frame, we need to interpolate the data in the frequency domain. We use a process called zero padding, so we just extend the length of the array. Now this turns out that it's equivalent to sin x over x, or sync filtering in the time domain, and this will interpolate the data to give us a higher resolution. So let's have a look at how that happens in the frequency domain. If we take our real and imaginary data, samples in the time domain. We perform our fast Fourier transform, we get the data into the frequency domain with our endpoint array. When we zero pad or interpolate, we get a factor of x multiplication on the length of the array. When we perform the inverse fast Fourier transform on that data, we end up adding in these extra samples, these filtered samples, into our time domain sequence. So a very similar process to the overlap and add, overlap and save type of thing. We've got time domain data coming in, fast Fourier transform, doing some processing, inverse Fourier transform, time domain data coming out that is now interpolated. And again, the key thing here is the massive improvement in the number of MIPS required to implement this process. There is a latency increase, but it's a block-oriented application anyway, so reducing the MIPS reduces the cost. So in this application, we were performing a windowing function, fourth order Blackman-Harris. Professor Harris's name comes up again, for far phase reverberations. We were then using the output of our frequency domain interpolation to do frequency domain correlation, as per the sort of overlap and add block previously, and that frequency domain autocorrelation gives us the time domain delta between the received pulses. So we send out a pulse, we get reflections and so on. By measuring the distance, the delta time domain between the primary pulse transmitted and received, we get the time of flight, and from there we can detect the structure of the material. Here's a diagram with a sort of summary of the main benefits. This is actually a diagram of the output cross-correlated data with the primary pulse cross-correlation and the secondary reverberations being shown. Okay, so that's autocorrelation and time domain interpolation. The last little application I'm going to talk about before we stop for questions is transducer frequency domain response normalization. And again, this was an application I was involved with a few years ago. We had a transducer that had a frequency response that was not very flat. Let's just put it that way. We needed to try and flatten the frequency response of the transducer that was being used in this application. So again, we could calculate the frequency response. We could calculate a filter, a time domain filter, that when we put the data from the transducer through the filter, the output would be a flatter spectrum than the transducer provides. But again, we have the problem that the filtering is a massively MIPS intensive task. So we actually researched whether we could use the fast Fourier transform for this kind of application, and indeed we did. We used one of the overlap techniques, and basically, as the if you think about the convolution in the time domain is equal to multiplication in the frequency domain. In this case, we want the opposite. We want deconvolution in the time domain because we want to remove the detector's response to make it flat. So we want to do deconvolution. So deconvolution in the time domain is equivalent to a division in the frequency domain. Now, of course, division operations have problems. Two particular problems. One is they're very expensive in terms of transistors to implement and time. The other thing is that dividing by zero causes all sorts of problems for processors which don't quite yet handle infinite number sequences. So we'll look at both of those problems in the next few slides. So the first thing we need to do is to be able to handle the divide by zero instance. And in this case, we basically had a limiter on the transducer impulse response that we were using, passing into the division operation that would limit the minimum value to effectively one least significant bit. So that we were never ending up, actually it was a minimum value, but effectively this reduced the possibility of removed the possibility of a divide by zero error. So we've removed that. What other problems with divide is noise. Even small amounts of noise cause problems when dividing by numbers close to zero. But the other problem is division is very slow. In this particular application, I pre-calculated the transducer impulse response, passed it to the frequency domain, performed the 1/x pre-calculation, so actually converted the division to a multiplication operation, and then was able to run that at full speed, full sample rate processing mode. But you can't always do that, so there are other algorithms, Wiener filtering, maximum entropy methods that can be used to overcome some of these problems. But for basic transducer frequency response linearization, this is a very, very handy process to be able to use. Here's the code. We're performing the fast Fourier actually this is the simulation code. This wasn't the real-time code, because remember, in my real-time code I pre-calculated the impulse response, pre-performed the division, and in the real-time code I performed a complex multiplication. But for the simulation I was just doing the whole process, so fast Fourier transforms, set the minimum value, complex divide, inverse Fourier transforms, and then actually I was just normalizing the FFT length as well, so that the end-to-end gain was 1. We haven't gone into this, but any DFT function, there's an end-to-end gain of n, where n is the size of the fast Fourier transform. So this divide here was at the bottom. They're handled separately because they're simply just to normalize the gain through the Fourier transform, inverse Fourier transform pair operation. Okay, that is the end of my talk. We've talked about using the fast Fourier transform for processing data in the frequency domain. It has many benefits, reducing MIPS, which obviously, and memory, which have a benefit of reducing the cost of our system, or enhancing functionality in an existing system with the same processing capability. I found them particularly useful in specialized applications, e.g. in narrowband applications. The very first time I used this technique actually was back in the days of wireline modems, for implementing a phase roll simulator in a voice band modem for a satellite communication link. So you can kind of see that this technique, it's a really powerful technique because if you can understand it, you can use it in so many different areas. Okay, final little note, the Fast Fourier Transform is not always the best solution. Sometimes the DFT is faster than the Fast Fourier Transform, but that's a little side note to leave you pondering. That's for another lecture. Okay, thank you very much for your time. It's been fun. We have questions and answers now. I'll stay on the line. If any of you have questions, please do not hesitate to get in touch. If I can help you with your DSP, your AI or machine learning, embedded systems projects, please do get in touch. Actually, as an aside, this presentation has been all about using the Fast Fourier Transform and frequency domain for enhancing and processing signals. I've got a paper coming up, a presentation coming up for the TinyML Foundation, looking at using the Fast Fourier Transform for machine learning application, pre-processing the data ahead of an AI system. We haven't got a date for that yet, but keep an eye on the tinyml.org website, and that will come up soon. And maybe if Jacob and Stefan are going to run this conference next year, by then I'll have more details to talk about that application, and maybe I'll present a paper on that at the DSP online conference next year. So thank you very much. Thank you very much to Stefan and Jacob for arranging this event. I know they've put a lot of effort into this. I know from my discussions with them. And yeah, have a great day. And we will now open this up for discussions and questions.